All right, fourth graders, here we are. Finally, we've reached the top facts and information that's key to our Module 4 on angles and planes and geometry. So I'm going to direct us to the important parts of the apps and lessons that you should be reviewing before tomorrow's actual final. And if you take a look at GeoGebra, this is the web app that I have shared with you multiple times. And I want to point out the ones that you should really be focusing on to get basic geometric objects. You should all know that's where we began. We have concept of points. So we have this concept here of a point. So that's just a single point in space. Think of it if you were floating in outer space, a little teeny dot, or you would say a single marble, it would be representing a point in space. And then moving on, we found out if you have 2 points in space, like B and C, then you would have something called a line. And that means this line, as you can see, it would travel on infinitely in either direction. So if there were an arrow we could draw on this, that arrow might be right somewhere near B, pointing downward to the left, and then another arrow would be pointing on from C upward to the right. The next concept that we covered that you should know is a segment. So a line segment is something that you might think of as 2 points on a ruler or 2 points on an object. Think about looking in your room or where you're at home, maybe the table, 2 points on the table. And they have finite positions. That means they stop somewhere. And that's because 2 points, when you connect a line in between, one straight line, you get a segment. Segment meaning a section or a portion of. Then comes the more interesting one, which is a ray, FG. A ray, as I say, maybe back in time that your parents were growing up, they thought of a ray gun. A ray gun means it actually has like a laser. And think of Star Wars, a laser starting from point F and blasting away through G and then continuing on all the way through G infinitely in one direction. So starting at F and continuing through G in a straight line and on infinitely down to the right maybe. Then here comes the interesting part, would be HIJ, these points here. You have H, you have I, and J. And when you have 3 points, you want to think of HI as one, say, line segment, and then JI as another line segment. And when these 2 line segments intersect or meet, in this case meet, what do you get? A vertex, and that's what you have shown here. And that vertex point I creates an angle between the line HI and JI, and that angle, it says right there, angle, is formed. So that's what we've been talking about, moving on from what a vertex would be. Okay, so we have the basics of geometry or geometric objects there. Then we move on to angles and measurements, so types of angles that exist. With types of angles, we know there are many types. We start here maybe with an obtuse angle, and then we move to the right angle, and we recognize, oh yeah, there is that symbol or that abbreviation with a square at that vertex point, A. Then we move further, and dropping less than 90, and it becomes acute, acute, small little acute angle there. That gives you that. And then if we move further all the way there, we have a straight line, BC or CB, and that straight angle we know must be 180 degrees. What if we go further? Suddenly, when we pass 180 degrees, angle CAB is formed, but I'm more interested in the angle that is, you want to say, on the top side where the green arc is drawn. That passes 180, doesn't it? So whatever the continued revolution as we continue forward onward to a final 360, you'll see how it can get very close. And once I cover up, it would be a 360. So following that motion, you should know all the names of the angles and the special types of angles. So let's look at it really quickly. We start on the quadrant 1 at 0 degrees. If we were on a protractor or measuring, we know we're in acute land. And then suddenly we're at right angle land, obtuse land, and then now we go further, and then it's reflex. The reflex meaning past 180 Anything past 180 and to close it off to the full revolution becomes the final revolution close at 360. Okay? All right, so now I will direct you to going further down. The others are there to just look at animated apps for obtuse and write, but we already saw that. So then you might want to look at Protractor Practice. And in Protractor Practice, you have a chance to choose a style, which probably looks like this. Realize that your protractor goes from 0 to 180 starting on the right or the left, because you know that you can measure angles with a protractor depending on what line segment or line that you're placing your protractor on. So let's take a look. Let's just do a quick one right here. We'll zoom in. We'll take our protractor, we'll place it over the point B, and then we want to get this angle that's in green with the arc figured out. Well, one way is just to line it up this, and then we find out, okay, 0 to 180, but we have more of an angle. It only goes to 180 on this protractor, doesn't it? So we have to continue on. And how could we do that? One would be take a ruler and then draw a line, and then continue on for that from that one where that 180 left off. See my red dot, and then measure further, and then you get somewhere in the 81. So we're talking 180 plus 81. We're in the 261 approximately, somewhere there. That's one way to measure it. But the more accurate way that I recommended, if you join me in our actual office hours, was not to measure using that full and then extension to add on to it, but to take your protractor, in this case, place your protractor in this position, line that up, get it accurate there, and then measure here. Now you get it to, you'll recognize this as 0, and then we're at like about 98 or 99, close to 98, 99 degrees. Then you just realize that, well, one whole revolution is 360 degrees. So how do you find the arc that is in the white space? We just did 98, and we subtract it from 360 to find the actual one that we're looking for. So 360, right, minus 98, and then you do the math. That gives you your actual answer. So somewhere around 261 degrees. Okay, moving on. There's some more fun things we can look at. I'll scroll down here. Sum of interior angles in a triangle. Well, this is a good review of what are angles in a triangle. And in this case, we have an equilateral triangle. How do I know that? Because all the angles are the same. And for all angles to be the same, then all the sides of this triangle also have to be the same. And that I know by experience. You're learning it for the first time, perhaps. But that's a rule. If all the angles are the same, that means the length of all those sides has to be the same as well. And there's certain theorems and rules you'll learn in high school geometry. Furthermore, you're looking at changing up this triangle. Okay, so I change the lengths, and I have something like a scaling triangle now, somewhere around there. And then I realize if I add all those degrees up here, angle A, angle B, and angle C, what would I get? Well, let's try adding them up. We have in the ones place, and we got about, well, it's approximately, let's try to get something close here. There you go. 90 plus 60 plus 30. We can do that mental math in our heads, and you're going to see it equals to exactly 180. So this app may be slightly off in some cases when you play with angles, but I know that this is a special angle, triangle, because the angle 90 is in it. So it's a right triangle, and it's a 30, 60, 90 right triangle that is formed. And this is we call it special because when we see this happen, we realize that the numbers have ratios or a comparison with lengths. So there's we say a 3, 4, 5 relationship. Okay. So I just want to point out, you can practice with this, and you know that all angles that are inside a triangle always must equal to 180, no matter how you play it. Okay, so there's that one. All right, so there you go. Okay, the next app that would be good for you to review let's go down, is looking at what are complementary or supplementary angles. So you can look at the missing complementary angle. What does it mean to be complementary? So here we have some angles formed here. Let's just do some checks here. So we have a cross section of the two line segments, and they intersect at C, and we have an angle formed that's 45 degrees. So that's angle ECD, and that says it's 45. But what would be angle ECB if you're looking up at the top right? That's where we're going to check it in a moment. Well, we know that if angle DCB, if you're following me, it says AB is perpendicular to CD. See, so number one on the bottom, line segment AB is perpendicular to CD. And that's very important to know that, because if it's perpendicular, we know it's 90 degrees of it. And so it forms a 90-degree angle, but we only know part of that. So the remaining angle is also, you'll see I'm moving that, 45 degrees, because it must be 45 plus 45 equals to a 90-degree angle. And we call this angle ECB complementary to the other angle ECD. Okay, so it's a complementary angle because it completes and complements to become 90. So you can play with this, and you can try different types of combinations yourself. Okay, supplementary angles. What are supplementary angles? Supplementary, you probably can tell right away. Angle AB, that's a straight line. And then we also therefore know that if it's a straight angle, the total arc is going to be 180 degrees, half of a circle, right? So if we want to change that angle, let's say we change it to something simple, like 90. And so the two dots indicate it would be a perfect 90-degree angle. And we know that 90 on angle, let's say ACD, the supplementary angle, which would be the one on the right side, BCD, must be 90 degrees. So what is the supplementary angle to 90 degrees? In a straight line or a straight angle would be 90. Because they added together, they both must come to a total of 180 degrees. Okay, so supplementary is always tied to what we know as 180. Complementary is always tied to a right angle or 90 degrees. Okay, so moving on, vertical angles. When you have two lines, in this case, they travel in both directions infinitely. So we have line CE and line BD, and they intersect at point A right here. Okay, when two lines intersect, you have something special that happens. They form 4 different angles. But even more unique or interesting is that those 4 angles that are formed are paired. And you can see that right here. It says measure of angle it says measure of angle DAC is equal to the measure of angle EAB, and they are both 45 degrees. So looking at that, what would you think happens to the other angles that are not drawn? You notice, so I'll call them out. EAD, can we figure out what that angle is? Well, we know that EC is a straight line, so EAD has to be the supplementary angle to 45 degrees. So what's that going to be? 135, because 180 minus 45 is 135. Then we ask ourselves, what about angle CAB then? And it's the same thing, isn't it? We can test that out 2 ways. One, we can look at the supplementary angle to EAB, and that would be 135 also. And so we therefore know the opposite angles of an adjacent side, which is, in this case, these 2 sides, CE or BD, have equal and opposite connection. They're equal, opposite, and they are the same angle. So we have 2 45-degree angles formed as shown above, And then we also have two 135-degree angles. So they're equal and opposite, these different angles formed on the cross section. So play with that and then test your knowledge. All right, moving on, you'll see here, there's a whole bunch of angles given in this diagram. We might play with them a little bit. Let's try getting a few different scenarios. Okay, so we have, let's get some rounded off numbers. 130 for one of the interior angles right here on the bottom left. The top one's 40 degrees. And then on the bottom, we could see that the right angle is formed. So it is a right triangle. It's also scaling because of the sides being all the different lengths. And it says, how can you find what angle ECD is? Right here up in the top right, it's covered up. Can you do it, given what we have on the diagram? Well, we know that the top angle, E, is 40, and the bottom one on the right is 90. So if we add 90 plus 40, you get 130. And that means by the rule of all triangle interior angles, you subtract that from 180 because all triangles interior angles must equal to 180 total. So therefore, what is angle C going to be? Let's go ahead and take a look. 50 degrees, right? Because 50 plus 140 is equal to 180. Then they have some other angles that you're looking for, such as EDC. And we already know that. It shows you right there that symbol. And so it has to be 90. And then how about EDB? Same thing. The symbol's already given, so that's also 90. All right, so play with this, change up some of these different angles or lengths of this triangle, and you can prove to yourself that no matter what you do with the lengths, so long as you have a triangle, you will always find that the interior angles equal 180, and then any angle outside of the triangle, such as the one that's a supplementary to this one here down on the left, angle C, it has to be totaled at 180 degrees. So one thing leads to another, in other words. So always think, the information given, you use that, analyze that, and then it tells you, based on the rules of either triangles, and we'll see quadrilaterals later, it tells you how to logically figure out what the other angles or associated lengths and angles are. Okay, now we're moving on to angles on the line. I'll just cover this real quick since it's there. So they give you a bunch of different slices of this straight angle on line AB, right? So you have all these different angles. Can you figure out the one that's missing? Well, certainly you can, because you know that the entire arc from point A, if we had a protractor right here, and then we followed it counterclockwise to B, right? We went from A to B, that it's going to be a total of 180. So to find out angle ECF, you know that you can add up all the ones given and then subtract it from 180 to give us the answer. In this case, we did it, it would be 37 degrees. Okay, so depending on what all these different angles are, you can play with it just to prove the point that no matter what you do, it has to come out to 180 when you add them all up. Likewise, what about if you were to want to find that different angles here? If I went further, then to complete the full revolution, I would have to subtract everything and then figure out what's left over by subtracting it from 360 degrees. Okay, so that pretty much ends the review on the basic geometries here that we discussed. You should now consider using your protractor and making sure you have a strong grasp or understanding of how protractors work. I would assume, because we already looked at all these other ones, it's fairly obvious that you can use your protractor to measure the actual rotation between 2 points on an arc. So here's the sample of playing with that. If they gave you a random angle somewhere, can you estimate that without using a protractor or try to guess it? That's what this game was about. So if you had a protractor and you want to measure starting on the left at 0 degrees, and then you need a little bit more clues, you keep hitting more info, and you find out, well, it's already past, it's somewhere between 45 and 90 degrees. How close? Well, now you see it's about 64 or so degrees. And you can keep going and going until you get the right answer. Okay. So that's as much as I want to cover with that content. Here in the apps for BrainPop, you might have fun to test your knowledge of sortifying, or sorting in this case, the different types of triangles. So I challenge you to play Sortify on BrainPop and have fun there on figuring out what your best score. How can you figure out what is your fast score to sort or classify these different types of triangles? Real quickly now, you could see, for example, if you put a right triangle in there, okay, and then you created a label, you're classifying, so you get a point for that. What about if we saw something like this triangle here? We recognize two sides were the same, and therefore it has to be an isosceles, so I get another point there. Same thing here. What about this one? All sides are the same. We know that to be equilateral triangles. I get another point. So play this game. It's really just testing you to see, do you indeed have mastery on identifying the different types of triangles based on side length. But it does show you the facts about quadrilaterals. So it says you want to classify quadrilaterals. Here's A through T, and then it gives you a ruler to double check that you're doing it correctly. So on the right side, there's various types of quadrilaterals listed by their name. Quickly now, just as a review, you know squares are quadrilaterals that have the exact same length for every side. Rectangles are quadrilaterals. The opposite sides are the same length, but they're not necessarily all the same, like a square. A rhombus, we said in our study that it kind of looks like a diamond, but if you turn it slightly to the right, and then you realize it does have same lengths, opposite lengths. And if you divided a rhombus in half, think of it, a food for thought, it would form two triangles on a line of symmetry. And you could have two lines of symmetry, like on this kite shape here. Parallelogram, the opposite sides, if you were to draw a intersecting line that's perpendicular to both, you figure out those lines are indeed going to go on forever and not touch each other. The two horizontals, or the two semi-verticals, those are parallel to each other. So opposite sides are parallel. So parallelogram, that's where it gets its name. We didn't really talk about trapeziums, but we know them as trapezoids. So trapezoid means all sides of this quadrilateral are different lengths. And then just the quadrilateral itself, here it has a unique shape. I think that's just a random call out being saying that all quadrilaterals must have four sides, and there's various types of angles in it. So take a look at this. Here's the ruler tool, and in A we know that is a rectangle, and rectangles, the interior angles are all right angles. So a right angle being 90, if there's four angles in every quadrilateral, 4 times 90 gives us a total of 360 degrees. So here's the challenge. That means all interior angles of any quadrilateral always must be 360 degrees. And then that way, if they want you to find an unknown angle, you'd have to be able to be given 3 out of 4 of those angles to figure it out. Otherwise, it would be impossible. Our final review in conclusion for Math Module 4 on angles and planes covered everything with regard to these lines, basic shapes in triangular and quadrilateral geometries, and then finally, how do we use these tools called protractors to be accurate, and rulers to accurately measure and determine what they are and the relationships they have. If anything, go back and watch some of the videos, play with GeoGebra, have fun with BrainPop, and we'll be looking for you tomorrow. Thanks for being strong and watching all those videos. And get ready next week to have lots of fun using your math skills to build something really cool and engineer with me. Have a great day.